Yes. So this team, the reliability analysis is very important topic. If it comes to the electrical system designing, mostly, if you are into the substation, if you are into the if you are doing the electrical designing part for a industry or for factories, it would be very essential one. This thing, and if you want to do this reliability analysis for our substation also, it's quite good. It's a good approach to do. You can give the justification, you can provide an optimized solution for the system. Like in nowadays, generally, for a substation, if I ask you to build a 200 megawatt of plant, wind or solar, generally all will go in a common design that they will go for 33 by 220 kV and having two transformers like 100 MVA for wind. Otherwise, for solar, they are having 4 into 80 MVA transformers. So this is a general practice I am seeing in my experience from the last 5 to 6 years. So I questioned that why I required to place four number of transformers. So until 2018, so this issue was not came up because the tariff rates are very good. There is a demand for solar and wind. There is a demand for electricity in India, power. The question was not came on the table. But a few years ago, after this pandemic and before the pandemic, this due to the decrease in the tariff rates for solar and wind in the mostly in, Indian projects, because of demand low and so many developers came into the market. So the question was put on the table, why now my tariff rate is only 1 rupee or 2 rupees? Again, for this tariff, this the old system, like suppose what I said before, 4 into 80 MVA transformers for 200 megawatt of substation. Is it the same applicable or a good option for this? So there is a question mark on this. Then this reliability analysis will guide us. No, no, no. 4 into 80 MVA transfer, 80 MVA design is not economical for this tariff rate, for this present scenarios. It requires, suppose, a 2 into 100 MVA or 1 into 3 into 80 MVA based on the tariff rates and project. And also, why required double bus with the main, but double main with bus coupler arrangement at my 220 kV system? So again, the question mark for the solar projects. Yes, solar, generally I am having the generation from morning 6 a.m. to evening 6 p.m. After that, there is a no generation. At this non-generation period, I can take the substation into the maintenance every day. So this is also gives a some view on that. Why to adopt a double main bus with for 220 kV system in solar for these tariff rates? Because now let's see, I am before I built a phone, I developed a mobile phone with some $100, and there in the market there is with some good futures and reliable with respect to the reliability, everything. I developed a product and I am selling that product in the market for $120. But at present scenario, this product, if I am selling for $120, no one is purchasing this. Now the demand of this product in the market is only $80. If it come for $80, they are ready to purchase. So then what I have to do? I should not compromise on the quality, and I should not compromise on the safety. So what should I compromise? I should compromise on the reliability. If this fail, so that the thing will comes, if I'm talking about electrical products. So I am decreasing the reliability because I should not decrease the quality. I should not decrease the safety. So I have to decrease the reliability. The reliability will comes down, and I developed the product again with some $65. So I am selling that product for $80 in the market. So which parameter changing this? The reliability. The reliability of the system will guide us. So what is the mark? What is the demand and what is supply thing? This curve can be maintained or can be maintained by this one of the factor of reliability. Fine. So that we discussed it in our last class. So that's a very important thing. And I would recommend you all the guys to read that IEEE 493 book if you have a time. Not now, after 3 months, 6 months, whenever if we having some time, please spend some time on that IEEE 493. Just suppose a 5 pages per day, it will takes in 1 month. You can read it off. It's like a novel kind of thing. Just don't need to memorize all those formulas and write. Oh, don't need this. Just see the flow. Just read it like a novel. Every IEEE document, you have to read it like a novel. So then you will get what is the synopsis inside it. What it's saying. What is the flow? That's enough for you. Suppose tomorrow, if you got a challenge, then no one in the outside will do by taking all the formulas. Just they will think that, okay, if this is a problem, okay, this book I have to refer because this problem was stated in that book. So I am opening that book and I will see the solution for this. Accordingly, I will prepare a solution for my problem. So this is the way of doing the engineering. So no one will memorize all the formulas and will do. So it's a kind of a guide. So, but you have to know what is inside that guide. Got my point in?
Yes.
Fine. So keep aside all these things. In yesterday's class, we discussed on reliability analysis. So from the reliability analysis, I want to conclude our LVAC SLD like this. Give me a minute, team. From the reliability analysis, I concluded this SLD for our project. Are you able to see my screen, team? This is the conclusion for my project. Why I concluded this is just for our next classes, we required sizing of all the things. In that context, I concluded this. But we have to conclude whether we require 2-number transformers and DG set, all these things by the reliability analysis. Just imagine that we have done the reliability analysis and we concluded this setup. Fine. Clear to you, team? Come to this single line diagram, team. So this is the low voltage AC single line diagram for my system. Low voltage AC distribution SLD for our substation. So here, if you see the scheme, this is again a general scheme you can see in most of the substations. They all follow mostly this scheme. Here I placing 2 number of transformers two number of transformers, and this transformer is connecting to this bus and feeding these loads, and this transformer is feeding these auxiliary loads, and I am having a DG set, and this DG set is feeding only the emergency loads. In a simple way, let me draw here in a simple way. So this is one of the transformer is feeding these loads, and this is one more transformer is feeding these loads, and I am having a DG set which is feeding some emergency loads. Now, first, let's see this. I am giving some X loads on this, and this is feeding some Y loads, and this is feeding some Z loads. Now, I am placing the breaker breakers here, one breaker, here one breaker, here one breaker, and here I am placing some switch here, and also I am having a DC DG generator. Here also I am having one switch. This is a manual. If you want to do the in automatic way, also you can do. It will give you an extra cost. You have to think whether it required a manual or auto here. How you know this? If you have to think when the DG set will come. When the DG set will come, let me tell you that. See, so this is a transformer 1, and this is the transformer 2, and this is the DG set. So this transformer 1, suppose, is feeding all the loads, X, Y, and Z loads. So if it has to feed all the loads, then this breaker should be closed, this switch also to be closed. And this transformer is not operating, so this will be in open condition. So this transformer is feeding all the loads by closing this breaker, and closing the switch. And after a few days, this transformer was failed. If this transformer was failed, then it has to be open up. Team, please mute your mics. Yeah. This has to be open up, and this should be closed. Now, this transformer is feeding all the loads. And I have not seen, because it is in normal position, after failure of this one, I charged this. Due to some, without testing anything, I charged this. So this transformer is also failed. Or not only transformer team, suppose the breaker failed, or this feeder, the cable failed, whatever it may be, we don't know. Whatever it may be, here, the system was failed. So now this transformer is failed, and this transformer is failed. Now the DG set will comes into the picture, and it will feed only my emergency loads. Only my emergency loads. Emergency loads generally for the substation, some lights, illumination, and relays, all these things. So for all the relays, actually, I required the DC supply. How I will get the DC supply? So this DG cell generator, again, I am having one AC supply, which is connected to the battery charger. One of the load in the jet is connected to the battery charger. This battery charger converting the AC to DC, which is having a rectifier inside it. It is converting the AC to DC. And this DC is distributing to all the relays. Now, if suppose the DG set is also failed, maybe due to some petrol or diesel was not there available, maybe some scenario, then this relays, but the relay should need supply continuously, because we have to provide a good reliable supply to the relays. So in that case, I am having one more setup for this, that is a battery bank. So the battery bank will be given to the bypass to this. So if there is a no supply from this, no supply from the battery charger, this battery banks will feed the supply to the loads up to some duration, like 3 hours, 5 hours. It depends upon your project requirement. So this is the setup team. So generally, what we will do is, what outside the developers will do is, they will run the both transformers parallelly, and they will open up this one. So this transformer is feeding all the loads, and this transformer is feeding these loads plus Z loads, Y plus Z loads. This transformer is feeding only X loads. Suppose any one of the transformer is failed, then this will be closed, this will be open. So in that case, the scheme will work here. And if both the transformers are failed, manually you are opening this one switch and you are closing this. So the DG generator will feed only the Z loads, which includes the battery loads. If this cable or battery charger failed or DG set failed, then the battery bank will feed the or these loads. So this is the entire a simple scheme for our AC and DC distribution. So if you see the scheme here, out of these 3 breakers, at any time, only 2 will be in closed position. Either this 2 or this 2 or this 2. So out of these 3, only 2 will be closed. So how can you do this? You can implement the soft logics, or generally to save the cost, we are having some mechanical interlock here. Like we will place, for 3 breakers, we are having 2 keys. Two keys. So if I insert key here and key here, then this will work and this will be in open only. If I want to this, I will remove this key and I will place this. So it will be. So in that way, we can do that. Mechanical interlocks we can do. Because it's a LVAC distribution, which not required much setup of control and protection, everything. So we generally it's adopted here. And for the DG set, manual closing switching is adopted. If you want automatic also, you can place. You can place the breaker here, or you can place the breaker here, and you can place some relay here. And this relay has to sense the voltage signals from this. If both the transformer, there is a no voltage signal, it seems that there is a no supply from the transformers. So if the no voltage, then the relay will pick up and this breaker will be closed and this breaker will be open. So you can develop the scheme in that way also, but it is costlier. So to make it simple, we are operating the DG set in manual, both the transformers working independently. If one of the transformer is failed, other transformer will take care of all the loads. If both transformers are failed, DG set will feed the emergency loads. If the DG set or the cable or the battery charger, whatever it may, any one of them are failed, then the battery bank will come finally and it feed all the emergency loads. Emergency loads in the sense, the only related to the control and protection. If you want to place the lights also, it's your wish. How you are designing how many loads you are putting on the battery bank, you have to consider. So this is the scheme. Same you can see here also. Let me see. So this is the scheme. What you are seeing here. Yes. So this is the transformer, which is 33 by 415 volts transformer, and the rating, vector group, and impedance we will discuss now. This is the 2 transformers are connected to the distribution board. This is the main AC distribution board, and from this it's connected to the inside this 2 breakers and 1 breaker. So these 3 breakers having some interlock, electrical and mechanical interlocks. In between the 3 ACBs, maximum 2 ACB should be closed. This is my interlock. And this feeding these loads, this feeding these loads, as well as the emergency loads. In the emergency loads, you can see what are the emergency loads? Lighting loads and inverters and 220 volt chargers, see, batteries. 48 full chargers for the OPGW for fiber optic telecommunication for SCADA purpose. And this is the DG set. The rating of the DG set, rating of the transformers, rating of the battery tank, we have to discuss in the coming sessions. We have to discuss this. So from this, it's again going to the next distribution board and from through various distribution boards. It depends upon how you are distributing the system. Suppose, let's see. So this is my AC distribution board, and this is my entire plant. This is my entire plant. I'm having a one motor here, fans here, and something. And I'm having some loads here, and some loads here, some loads here, and some loads here. So I am placing a AC distribution board here. So what I will do, I am taking one connection to here. I place some distribution board again, sub distribution board. And from the sub distribution board, it is connected to the motors and it's connected to the switchboards. And these switchboards, it's connected to the fans, lights, everything. Similarly, I'm having one more sub distribution board here and from here to here. So like that. So this is the how you are doing this. If you're having a small sub-distribution boards, what is the benefit over here? The cable cost will decrease. Suppose if you are not having this, if I are having 10 loads here, each load you have to give the supply, you have to give the cable from all the 10 loads. See, 10 cables has to run. But if you have a sub-distribution board in the middle, only one cable. So you can reduce the cable cost as well as the cable trench civil costs. Just you are increasing one panel, which will cost you 7,000, 9,000 rupees, 10,000, small panels. This is one panel. So this is how you are distributing. So in this, what will be, you can see in the main distribution boards, you can see the air circuit breakers, what I shown before. And apart from that, MCBs. But in all this, you can see only MCBs and MCCBs. That's it. No other things will be there in all these distribution boards. Unless if you suffer the lights, suppose if you want to turn on the lights after 6 p.m. automatically, if you want to include some timer circuits, you can add the timer circuits inside these distribution boards. To the lighting panel, to the lighting boards. That's up to your space. If you are not having this, only MCBs will be there inside this. MCBs or MCCBs. Depends upon the rating of the load connected to that. Clear, team?